logic, a counter is a device which stores and sometimes displays the values of a number of times the event has occurred. The most common type of digital circuit is a sequential circuit, which consists of one input line, which is a clock, and several output lines. A counter generally consists of several flip-flops which are arranged in a cascade. Counter is very important and can be used as a separate integrated circuit and sometimes as a part of an integrated circuit.
D-type flip-flops. The D-type flip-flop has one data input D and a clock input. The circuit H triggers on the clock input. The flip-flop also has two outputs Q and Q dash, where Q dash is the reverse of Q. The operation of D-type flip-flop is as follows. Any input appearing at the input D will be produced at the output Q in time t plus 1. For example, if in the present state we have D is equal to 0 and Q is equal to 1, the next state will be D is equal to anything and Q is equal to 0. Knowing the above, we can now generate the state change table and the operating characteristics. The operation of the D-type delays any input by exactly one clock cycle. Several D-type flip-flops together can produce delaying circuits. Possible applications for matching time delays in digital television systems.
Ring counter is a type of counter composed of flip-flops connected to shift register. Output of the last flip-flop is fed as the input of the first flip-flop, forming a ring structure. There are two types of ring counters, a straight ring counter and a twisted ring counter. The straight ring counter is also known as one-hot counter, where the output of the last shift register acts as the input of the first shift register, circulating single bit once. A twisted counter is also known as Johnson counter, where the complement of the last output acts as the input of the first shift register, followed by a series of ones and zeros. A ring counter is generally used in hardware device to create a finite state machine. A binary counter represents 2 to the power n states, where n represents the number of bits in a code. A single binary counter represents n states, whereas a twisted counter represents 2 n states.
Now we are going to show the real-time working of a ring counter. Over here, we have all assumed the role of D flip-flop, a very essential component in the making of counters. In this ring counter, we have connected the output of the last flip-flop to the input of the first flip-flop, thereby forming a ring. For demonstration purposes, we have assumed that in the video, the notebooks have the value of logic 0 and the bottle have the value of logic 1. When the first positive edge of the clock pulse is received, the first flip-flop in the sequence, which is already preset with logic 1, sequentially transfers its data to the second flip-flop, and so on and so forth, till the last flip-flop transfers its data back to the first flip-flop. This same process keeps on happening for every clock pulse trigger, as we can see in the video. Finally, in the end, the last flip-flop, which holds the bottle logic 1, transfers its data into the first flip-flop, thus completing the transition cycle. And therefore, we observe that we have counted from 0 to 3, which is 4 transition states with the help of a ring counter. Thank you.